Uh, Good afternoon, students. Today we are going to continue the last session. In the last session, we started the instruction set of the 8086 microprocessor. Under that, we studied about the data transfer instructions and we started the arithmetic instructions. I think in the last class we covered the addition instructions also. So here addition, ADC is nothing but addition along with the carry. INC is nothing but increments the destination by 1 every time upon every execution. D is nothing but the decimal adjustment after addition, which is used for in BCD arithmetic operation. So in order to show the result in the BCD form, we are going to make use of the DAA instruction. And after that, we are having the AAA instruction, which is nothing but ASCII adjustment after addition. Okay. So in the today's class, we are going to concentrate on the subtraction operation. We are going to concentrate on the subtraction operation. Okay. So subtraction operation. Okay. So for subtraction, the first instruction is going to be the SUB instruction. So SUB, if at all I am going to take it as a destination, comma, source, destination, comma, source, then what it is going to do means, this is the syntax for the subtraction operation. So it is going to be, perform like this. So it is subtracting the destination. It is going to subtract the destination from the source. It is going to subtract the it is going to subtract the source from the destination, and stores the final result in the destination. Okay, minus so okay. So this is what the syntax. So subtraction operation is nothing but it subtracts the source content from the destination, and final result is going to be stored inside the destination. Okay, now so we have one more instruction called as one more SUB instruction called as SBB. So we have one more SUB instruction called as SBB. So SBB, again the destination comma source. The difference between these two instructions, SUB and the SBB, is in SBB case, the instruction means microprocessor is going to be subtracts the source value from the destination along with the carry flag. Microprocessor subtracts the source value from the destination along with the carry flag. Okay, now so if you want the explanation for that, I'll take the red to differentiate that one. Okay, so destination is equals to destination minus source minus carry flag. Okay, now SUB instruction is going to be subtract the source from the destination, but SBB instruction is going to be subtracts the source from the destination along with the carry flag and updates all the conditional flags. It is going to update the conditional flags. Okay, now except the parity flag, all the flags are going to be updated. Okay, now so that is what the SBB instruction. Similar to this, we are having one more instruction called as a DAS instruction. So DAS instruction, yeah. So just remember these two instructions. We'll go back to our slide. So SUB instruction is nothing but so subtracts the source from the destination, and then final result is going to be there in the destination. SBB instruction is nothing but so subtracts the source from the destination along with the carry flag and stores the final result in the destination. After that, we are having the one more instruction called as a DEC. Okay, now decrement instruction. Okay, now we have one more instruction called as a DEC. So syntax for this one is going to be the DEC instruction, which is a decrement operation. So syntax is destination. Okay, now syntax is going to DESTN is nothing but I'm just assuming it as a destination in short. Okay, now so decrements the destination content by 1 upon every execution. So for example, so destination is going to be stored with the decremented value of the destination. Upon every execution, it decrements the destination value by 1 and stores the result back into the destination this instruction is also going to update all the flags except the carry flag. After that, we have one more instruction called as a what is that, DAS, decimal adjustment after subtraction. So it is just like a DAA, decimal adjustment after addition. Just like the DAA instruction, we have the DAS instruction, which adjusts the result into the decimal format after subtraction. After that, we are having the AAS, ASCII adjustment after subtraction. AAS is nothing but ASCII adjustment after subtraction. Means if you want to show the result in the form of the ASCII value, we are going to make use of the AAS instruction. After that, we are having the NEG instruction, which is nothing but the negation. So NEG is nothing but which is a negation instruction. Okay, now it is a negation instruction. Negation means it is going to be performed. The syntax for this one is going to be the negation. Syntax for this one is going to be the destination, right? The syntax for this one is going to be the, it is going to be replace the destination with the with its 2's complement. So 2's complement value, 2's complement of destination. So if you want to see that one, I think you can't see the screen as we move on. So 2's complement of DESTN. Okay, now I'm expecting that you are able to see the destination. Okay, now so negation operation is performing the 2's complement on the destination and stores the result into the destination itself. So that is about the negation instruction in subtraction case. So the next case is we are having the multiplication operation. Multiplication. Okay, now so here the microprocessor is able to perform. In case of the 8085 microprocessor, we don't have the multiplication operation, but in case of the 8086 microprocessor, we are having the multiplication operation. There are two types of multiplication operations going to be performed by the 8086 microprocessor. One is the signed multiplication between the signed numbers, multiplication between the unsigned numbers, multiplication between the signed numbers, multiplication between the unsigned number. So if you want to show one of the number as a unsigned number, let us suppose I am assuming that I am just taking one example. So I am assuming that I have one 8-bit number. So I am just taking one 8-bit number. Okay, now so in this 8-bit number, if I am trying to this is a 8-bit number, now I am just using the 8-bit data. I am having one 8-bit data. Let us suppose I am having the 8-bit data. Now I am going to write the bit format for that. So I'm just writing the bit format D7 space D6 6th bit position, D 5th bit position, D 4th bit position, D 3rd bit position, D 2nd bit position, D 1st bit position, D 0th bit position. Okay. So here as I said, we are having the two types of multiplication. So one is a signed multiplication, another one is the unsigned multiplication. In order to differentiate what exactly the signed number and what exactly the unsigned number, I just took the 8-bit number. Same explanation is going to be applicable for the 16-bit number also. Same application is going to be same explanation is going to be applicable to the 16-bit number also. Okay, now so as we know that this one is going to be the what is that most significant bit. The D7th bit is going to be the most significant bit, and the D0 is going to be the least significant bit. D7 is going to be the most significant bit, which is nothing but the MSB. D0 is nothing but the least significant bit, which is nothing but the LSB. Okay, now so if at all the bits, whatever the 8 bits are there from the D7 to D0, if at all these bits are representing the value, then it is called as a unsigned number, unsigned 8-bit number. Okay, now means in an 8-bit number, if all the bits are representing the value, if all the bits are representing the value from D7 to D0, then this number is called as a unsigned number. This number is called as a unsigned number. It is going to be the unsigned number. Now, if at all we are interested to show the signed numbers, if at all we are interested to show the signed numbers, unsigned numbers are nothing but if I am having the 8-bit number, then all the bits are going to be represent the value. If I am having the 16-bit number, then all the bits are going to be represent the value. Then it is called as a unsigned numbers. If I am going for the signed number means I would like to show that whether the number is a positive number or the negative number. Means I would like to show the number along with its sign, whether it is a positive sign or the negative sign. So for that, what I'm going to do means here we are going to make use of means if I'm having the 8-bit number, I would like to show the 8-bit signed number. I would like to show the 8-bit signed number. So let me write signed number. If I would like to show the 8-bit signed number, at that time, here we are interested in showing the 8-bit number now. Out of 8 bits, 7 bits, out of 8 bits, 7 bits are representing the value. So I'm just taking these number from D0 to D7. They are from D0 to D6. They are representing the value. They are representing the value, and the most significant bit is going to represent the sign of the number. Most significant bit is going to represent the sign of the number. Similar to similar, this is the explanation for the 8-bit number. If you are going to the 16-bit number, then the D15th is the most significant bit, D0 is the least significant bit. At that time, D15th bit in the 16-bit number combination is going to represent the sign of the number. So in this case, D7 is representing the sign of the number, and remaining D6 to D0 are representing the magnitude of the number. Okay, now. So if at all, that means signed numbers are nothing but we are showing the value along with its sign, whether the number is a positive number or the negative number. Okay, now if at all this particular D7th bit position is equals to the 1 in the signed numbers case, if at all this D7th bit position is equals to the 1, then the number is called as a, then the number is a, then number is a negative number. Number is a negative number, means whatever the quantity which is going to be specified by from the D6 to D0, they are going to be the, this number is preceded with the negative sign, preceded with the negative sign. Okay, now so that is the use of the most significant bit in the signed numbers case. So in the signed numbers, if at all the D7th bit position is equals to the D7th bit position, uh, D7th bit position is equals to the 0, then the number is positive number. Number is a positive number. Okay, now then the number is called as a positive number. This quantity D6 to D0 combination is showing the positive number. Okay, now it is going to show the positive number. The difference between the signed numbers and unsigned numbers means, if we are taking the 8-bit number, in case of the unsigned numbers, if we are taking the 8-bit number, then all the bits are representing the value. Okay, now we don't have any sign, so we don't have any sign means it is going to be obviously the, by default it is going to be the positive number. If we are interested to show the sign of the number also, then at that time we are going to take in any bit combination. If it is in the 8-bit combination, I am going to take the MSB bit position to represent the sign of the number. If it is a 16-bit combination, I am going to take the D15 as a MSB bit to show the sign of the number. So if at all this bit position in the 8-bit combination, I would like to show the signed numbers na, in the 8-bit combination. If at all the D7th bit position is equals to the 1, then whatever the quantity we are having, that is going to be the negative number. If at all the D7th bit position equals to 0, then whatever the quantity which is going to be specified from the D0 to D6, it is going to be the positive number. It is going to be the positive number. Now, this is what we are having the signed and unsigned numbers in case of the 80, not only in the 8086 microprocessor, in any case we are having the signed numbers and the unsigned numbers. Okay, now. So now here what I'm interested is, I would like to explain one concept called as a multiplication instruction, right? We are interested to explain the see the multiplication. Okay, so wait a minute, I'm interested to show the multiplication operation, right? So multiplication, so we are interested to see MUL instruction. So MUL followed by source. Syntax for the MUL instruction is MUL followed by source. SEMA, MUL instruction is used to perform the signed multiplication operation. MUL instruction is used to perform the signed multiplication operation. And we have one more instruction called as the IMUL. IMUL, syntax is IMUL space source. So IMUL instruction is used for performing the multiplication between the signed numbers. MUL instruction to perform the multiplication between the unsigned numbers, and IMUL instruction is used to perform the multiplication between the signed numbers. Multiplication between the signed numbers. Now you may ask me one question, sir. Whenever we are taking one instruction, obviously we are supposed to have the destination as well as the source, but here we don't have the destination in the syntax. Why we are not having the destination in the syntax? So as I said, we are having the accumulator, which is going to be the mandatory operand in in some of the instructions. So the some of the instructions, the accumulator lower byte is going to be accumulator lower byte as well as accumulator 16-bit format is going to be the destination in some of the instructions. So in those instructions, MUL means in case of the multiplication as well as the division, in both operations, destination is going to be the accumulator. It is a mandatory one. Destination is going to be the accumulator in multiplication case as well as the division case. In both cases, destination is going to be the accumulator. Okay, now. So here in 8086 microprocessor, as we have seen that MUL is performing the unsigned multiplication operation, that is a multiplication between the two unsigned numbers, IMUL is performing the multiplication between the two signed numbers. And we are supposed to know one more point regarding the multiplication. Whatever the multiplication instructions which are there in the 8086 microprocessor, they are able to perform the 8-bit cross 8-bit multiplication. Means they are able to perform the multiplication between the two 8-bit number or multiplication between the two 16-bit numbers. Multiplication between the two 8-bit numbers or multiplication between the two 16-bit numbers. Again, I am saying that multiplication operation which is there in the 8086 microprocessor is able to perform the multiplication between the signed numbers as well as the unsigned numbers, and also the multiplication operation which is there in the microprocessor, it is able to perform 8-bit multiplication operation or the 16-bit multiplication operation. Okay, 8-bit multiplication operation and the 16-bit multiplication operation. So here if I am taking the MUL, for example, I am taking the MUL. Okay, so MUL, I would like to perform the 8-bit multiplication operation. So source operand should be the 8-bit. Now the question comes that how exactly the microprocessor is going to be decides whether the microprocessor need to perform the 8-bit multiplication or the 16-bit multiplication. That purely depends on your source size. As a part of the instruction, if you are specifying the source as the 8-bit number, then the destination is going to be the 8-bit number. So this one is going to be the destination. So in the 8-bit multiplication, this one is going to be the destination, this one is going to be the source value, and here also this one is going to be the destination, and this one is going to be the source value. In the 8-bit multiplication, 16-bit multiplication, both operands should be of same size. So if how the microprocessor is going to be decides whether it is a 8-bit multiplication or the 16-bit multiplication, that purely depends on the source size. For example, so if I'm writing the instruction like this, if I'm writing one instruction MUL space BL. So what is the BL actually? BL is a 8-bit register. What is the BL actually? BL is a 8-bit register. Okay, now it is a 8-bit register. Now, as it is a 8-bit register, destination is going to be decided by the microprocessor as a 8-bit number. That destination is nothing but AL. In simple short, whenever you are writing the MUL space BL. So let me rewrite this one. Whenever you are writing the MUL space BL, then microprocessor is going to be perform some multiplication between the two 8-bit numbers. One of the 8-bit number is taken from the AL and another 8-bit number is going to be the BL, which we specified as a part of the instruction. Over here we specified the 8-bit number now. So as the BL is a 8-bit number, then the microprocessor is going to be takes the AL content because it is able to perform the 8-bit multiplication or the 16-bit, but it is unable to perform the 8-bit 16-bit multiplication like that. Okay, now so microprocessor is able to perform 8-bit multiplication or the 16-bit multiplication. So depending on the source size, destination is going to be decided. If at all the source is the 8-bit number, BL is a 8-bit number, then the destination is going to be the A. Destination is going to be the another 8-bit number which is there in the AL, and it is going to be default register taken by the microprocessor when it is performing the multiplication operation. One more thing is we will see the 16-bit multiplication also. One more thing is when you are performing the multiplication between the two 8-bit numbers, when you are performing the multiplication between the two 8-bit numbers, then the result is going to be what? Result is going to be the 16-bit number. Then where exactly the result is going to be there? It is there in the destination, but in this case the destination is going to be the 16-bit number. So as we are using the AL 8-bit multiplication, destination is going to be stored inside the AX register. Because AX is a 8-bit number. Sorry, AX is a 16-bit number. So means when it is performed, when the microprocessor is performing the 8-bit multiplication operation, then the result is going to be the 16-bit number. That result is going to be stored inside the AX register. For example, in the program, if you are writing in the instruction, if you are writing the instruction like this, MUL space BX. So here the operand size is what, ma? This is the source, na? So as per the syntax, syntax is nothing but this one is saying the mul space source. Okay, now as per the syntax, bx is a source. Destination should be what? Another 16-bit number, because source is a 16-bit number now. Because of that, destination should be the 16-bit number. At that time, the AX content is going to be taken by the microprocessor to perform the 16-bit multiplication. So again, I'm saying that size of destination is going to be decided by the size of the source. If the size of the source is the 8-bit number, then the destination is going to be the AL. If the size of the source is the 16-bit number, then the destination is going to be the AX register. So it is going to be the AX register, means it is going to be performs the multiplication between the AX number, between the two 16-bit numbers, performs the multiplication between the two 16-bit numbers. So here, when we are performing the multiplication between the two 16-bit numbers, now result is going to be the 32-bit number. When you are multiplying the two 8-bit numbers, result is going to be the 16-bit number. So that result is going to be there in the AX register. When you are performing the multiplication between the two 16-bit numbers, when you are performing the multiplication between the two 16-bit numbers, result is going to be the 32-bit number. Now the question comes that, do we have any register whose size is the 32-bit? We don't have any register whose size is a 32-bit. Okay, now, whose size is a 32-bit. That's why what the microprocessor is doing is, upon the 16-bit multiplication, result is going to be stored in two registers. Result is going to be stored in two registers. Okay, now, so those registers are nothing but the registers are dx colon ax. This one is going to be stores the result. Okay, now, so when the microprocessor is performing the 16-bit multiplication between the two 16-bit numbers, result is going to be the 32-bit number. That result is going to be stored in the form of dx and ax register form. So in this case, dx is holding the higher order word, ax is holding the lower order word, because the 32-bit number is nothing but what? It is going to be vary from, so let me show you that. Wait, I'll take the green. Okay, let me show you that 32-bit number is going to be the 31 to, varying from 31 to 16 and 15 to 0. Okay, now, so here it is a 32-bit number now. So out of 32 bits, these bits, out of 32 bits, the bits from 15 to 0, I'm just writing the d suffixes, d0, d0 to d15, d16 to d31. So totally it is a 32-bit number. So the 32-bit number is there now. 32-bit number is split into two words format. First word is a 0 to 15, and second word is going to be the 16 to 31. Second word is going to be the 16 to 31. Obviously, this word is called as a lower word. This word is called as a lower word. This one is called as a lower word, and this one is called as a higher word. Okay, now, this one is called as a higher word. Okay, now, so as we are having the 32-bit combination, lower word in the 16-bit multiplication, lower word is going to be stored. The result of the 16-bit multiplication, lower word is going to be stored in the AX register. Higher word is going to be stored in the DX register. Higher word is going to be stored in the DX register. Okay. So in brief, multiplication operation is nothing but 8086 microprocessor is able to perform the multiplication operation between the signed numbers as well as the unsigned numbers. Signed numbers as well as the unsigned numbers. So unsigned numbers are nothing but all the bits are representing the value. Signed numbers are nothing but most significant bit is representing the sign of the number. Rest of the bits are representing the magnitude. Okay, now, so here the multiplication instruction which is there in the 8086 microprocessor is able to perform the 8-bit multiplication as well as the 16-bit multiplication. That may be the signed numbers or the unsigned numbers, whatever the number it is, but it is able to perform the multiplication between the two 8-bit numbers or between the two 16-bit numbers. Okay, now again, so if you are taking whether the microprocessor is performing the 8-bit multiplication or the 16-bit multiplication, that purely depends on the size of the source which you are representing as a part of the instruction. If the size of the source is a 8-bit number, then the multiplication is going to be the 8-bit multiplication, means it is taking the AL content as a destination and BL content as a source, performing the multiplication between these two. When we are performing the multiplication between the two 8-bit numbers, the result is going to be the 16-bit number. So that 16-bit number is going to be stored inside the AX register. Now another case is if we are having the 16-bit number, means if the source is going to be the 16-bit number, then the destination is going to be the 16-bit number, which is nothing but the AX. Okay. So if the source is a 16-bit, destination is going to be the 16-bit, which is nothing but the AX register. It is going to perform the multiplication between the source and the destination. Final result is going to be the 32-bit number now. So in that 32-bit number, higher order word is going to be stored inside the DX register, and lower order word is going to be stored inside the AX register. Okay. Now, so means the result of this particular multiplication is going to be the result of the 16-bit multiplication is going to be represented using two registers combination, DX colon AX. We are representing like this. DX colon AX is a 32-bit result, which is storing the result of the multiplication between the two 16-bit numbers. Multiplication between the two 16-bit numbers. Okay. So this is what we are having. This is a multiplication instruction. What we are having in 8086 microprocessor. Okay. Clear? So 8086 microprocessor is able to perform the 8-bit multiplication as well as the 16-bit multiplication. Similar to the MUL, we are having the IMUL. Same concept. 8-bit multiplication in place of the MUL, we are going to have the IMUL. In place of the MUL, we are going to have the IMUL. That's it. Sorry. In place of the MUL, we are going to have the IMUL. Okay, that's it. We are going to have the IMUL. Everywhere we are going to have the IMUL. Explanation is same. 8-bit multiplication as well as the 16-bit multiplication. Result is going to be the 32-bit number. Okay, now in short, if you want to know this one, in short, 8-bit multiplication. In short, in short, AX is holding the result of the 8-bit multiplication. 8-bit multiplication. 8-bit multiplication. 8-bit multiplication. So 8-bit multiplication result is a 16-bit number that is going to be stored inside the AX register. 16-bit multiplication, at that time the result is going to be stored using the two registers, DX register and the AX register. Okay, now DX register and the AX register. DX register is holding the higher order word. AX register is holding the lower order word. So multiplication is between the two 16-bit numbers. Okay, multiplication between the two 16-bit numbers, right? 16-bit number. In short. Okay, so this is what we are having about the multiplication instruction in 8086 microprocessor. Another case is a what is that? DIV instruction. Another one is a DIV instruction. Okay, division operation. So let us go for the division instruction. Okay, so DIV, again the DIV is also we have DIV na. So DIV is also, there are two types of instructions for the DIV and the IDIV. Means division between the signed numbers, division between the unsigned numbers, and the division between the signed numbers. DIV is performing the division between the unsigned numbers. IDIV is performing the division between the signed numbers. Now, what type of divisions are able to perform by the 8086 microprocessor is a question. Okay, what kind of division operations it is able to perform? So 8086 microprocessor is able to perform the division operation using the two instructions, DIV and the IDIV. One for the signed numbers, another one for the one for the unsigned numbers, and another this one for the unsigned numbers. Remember this one. This one is for the signed numbers. This one is for the signed numbers. These two instructions are able to perform the 16-bit by 16. 16. It is able to divide the 16-bit number with the 8-bit number, or I'm going to take some gap. 8-bit number or it is able to perform the divide the 32-bit number with the 16-bit number. Okay now. So 8086 microprocessor is able to perform the division between the 16-bit number and the 8-bit number, or 32-bit number and the 16-bit number. Means numerator, if the numerator is the 16-bit number, then the denominator should be the 8-bit number. If the numerator is the 16-bit 32-bit number, denominator should be the 32-bit number. So syntax for this one is going to be the div instruction, right? Div instruction, div, syntax is div space, again source, again source, div space, let me take the simple one, source. Okay, so which means whenever you are trying to execute this operation, if the source is a 8-bit number, means if this one is a 8-bit number, obviously this one is a 8-bit number, then the numerator means source is nothing but the denominator. In the division, source is nothing but the denominator. So if the source is a 8-bit number, then the numerator is going to be the 16-bit number. If the source is a 16-bit number, then the numerator is going to be the 32-bit number. So if at all the source is 8-bit number, so let me take source is 8-bit number, source is 8-bit number, 8-bit number, then source is a 8-bit number now, then it is a numerator. If the source is a 8-bit number, numerator should be source is a denominator, numerator should be the 16-bit number now. That number is nothing but, so x is holding 16-bit number. Okay, x is holding the 16-bit number. No sir, we are getting confused. Then in short, I'm going to write one thing. Wait a minute. Control E, control R. Okay, so let me write. We are having the two instructions. No need to rewrite that one. So let me write one first instruction, which is not the div. I'm just taking one instruction, source. So if source is a 8-bit number, 8-bit, then the division is going to be I'm changing the color for differentiating that one. Division is going to be it is going to divide, means the 8-bit source is dividing the 16-bit number, which is nothing but the AX number. It is going to divide the AX content by source. Okay, so it is like what is going to be like, say, dividing the 16-bit number with the 8-bit number, So it is dividing the 16-bit number with the 8-bit number. If at all the source is a 16-bit number, okay now. If, let me take, source is a 16-bit number. If the source is a 16-bit number, then the division is going to be is 32-bit by 16-bit number. Source is a 16-bit number now, so it is going to be perform the 32-bit number by 16-bit number. That 32-bit number is nothing but is a dx colon, or otherwise I'll take one bracket to differentiate that. Dx colon ax content is representing the 32-bit number. This number is divided with the source. Because source is a 32-bit source is a 16-bit number. Means this division is whatever the division we are writing over here, I'm going to write upward. So this division is performing the, I'll take the green, this division is performing the, what kind of division it is? 32-bit by 16-bit division. 32-bit by 16-bit division. Okay, so this is what the division operation. Okay, so if the source is a 8-bit number, then the numerator is going to be the AX. If the source is a 16-bit number, then the numerator is going to be the DX colon AX. These two registers are showing the numerator. These two registers content is showing the numerator, and that too it is forming the 32-bit number. Okay, now, so that's why it is a 32-bit by 16-bit division operation, and this one is going to be the, as the source is a 8-bit number, then the division between the division is going to be the 16-bit by 8-bit division. Division is going to be the 16-bit by 8-bit division. Okay, now, so this is about the division operation. Now the question comes that soon after we perform the division operation, division between what ma? AX by source, or in case of the 16-bit by 8-bit division, in case of the 16-bit by 8-bit division, AX is holding the 16-bit number, source is holding the 8-bit number. In case of the 32-bit by 16-bit division, then DX AX is holding the 32-bit number and the source is a 16-bit number. After performing the division operation, we are having the result now. So we are having the result, right? We are having the result. Let me take this one again. We are supposed to discuss one thing. After performing the division operation, we are having the remainder as well as a quotient. We are having the remainder as well as a quotient. Okay, now, so here when you are performing the 16-bit by 8-bit division, 16-bit by 8-bit division, 8 okay 8-bit division. When you are performing the 16-bit by 8-bit division, obviously we know that it is going to be between the AX slash source content. I'm not interested, but let me rewrite in order to realize it is going to be very comfortable, right? So for this operation, we are having the quotient as well as the remainder now. So I'm just taking the red color. So in this case, in this 16-bit by 8-bit, who is holding the quotient, who is holding the remainder is a question. Okay, so quotient is going to be there. I'm just writing the Q. Q is going to be there in the AL register, and remainder is going to be there. R is nothing but the remainder. Remainder is going to be there in the AH register. In 16-bit by, remember ma, in 16-bit by 8-bit multiplication, we are having the quotient as well as the remainder. Quotient is there in the AL register, remainder is there in the AH register. Quotient is there in the AL register, remainder is there in the AH register. Why I'm explaining this much of, why I'm giving this much of explanation regarding these two instructions, nothing but for the first time you are facing the, you are coming across the multiplication and division instruction, and also we are having some programs on the multiplication division operation in the lab session. So that's why I'm just giving the more detailed explanation about this one. Okay, but if anyone comes for Viva, they are going to focus on this one only, upon division, in which register we are having the quotient and in which register we are having the remainder. Okay, so here we are having the 16-bit multiplication, 16-bit by 8-bit division. In 16-bit by 8-bit division, Q is holding the AL is holding the quotient, H is holding the remainder. Now if you go to the 32-bit number, if you go to the 32-bit number, that is nothing but 32-bit divided with the 16-bit number, right? 32-bit is divided with the 16-bit number. As you know that 32-bit number is nothing but TX colon AX divided with the source, which is a 16-bit number, right? Which is a 16-bit number. In this case, when you are performing the 32-bit by 16-bit division operation, in this case, the quotient is going to be there in the quotient, right? Quotient is there in the Q. Let me take the Q. Quotient is there in the AX register. Quotient is there in the AX register, and remainder is there in the DX register. Quotient is there in the AX register, remainder is there in the DX register. So this is all about our multiplication and division instruction in detail. So 8086 microprocessor is supporting the multiplication division operation. So the multiplication division operations are able to perform the respective operations like multiplication division between the signed numbers as well as the unsigned numbers, between the signed numbers as well as the unsigned number. When you are taking the multiplication operation, microprocessor is able to perform the 8-bit multiplication. Result is a 16-bit number that is going to be there in the AX register, and it is able to perform the 16-bit multiplication. Result is a 32-bit number that is there in the DX colon AX combination. Okay, if you are taking the division operation, the 8086 microprocessor is able to perform the 16-bit by 8-bit division, or it is able to perform the 16-bit by 8-bit division. So we are having on the screen itself, right? It is able to perform the 16-bit by 8-bit division or 32-bit by 16-bit division. 32-bit by 16-bit division. So in case of the 16-bit by 8-bit division, we are having the two results. After division, we are expecting the quotient as well as the remainder. Quotient is there in the AL register, remainder is there in the H register. In excuse me, in 32-bit by 16-bit division, quotient is there in the X register, remainder is there in the DX register. Okay, now so this is all about our the instructions, which are the multiplication and division instructions in 8086 microprocessor. I hope the video is very little lengthy one, so we'll continue in the next session with another kind of instructions which are there in the 8086 microprocessor, right? Okay, we'll continue in the next session with bit manipulation operation. Okay, thank you. If you are having any queries regarding this particular class, then you can ask me in the WhatsApp group. Don't worry about it. Okay, now, I'll take care of everything, but I'm just giving the in detail explanation. It is necessary for us. Okay, now, that's all for today's class. We'll continue in the next class.